Okay, so well, welcome back, everyone. So it's my pleasure to introduce Desmond Elliott. So Desmond is a professor at Copenhagen. So there he works on problems related with multilingual and multimodal machine learning. So he has extensive research on these topics. For instance, he's now running a largest project concerned with trying to model language with images and pixels rather than discrete tokens. And well, this talk here is going to be about vision and language. So a new topic that we introduced this year in the school. So I hope you enjoyed the lecture. Thanks, Desmond. Let's welcome Desmond.
Thank you for the introduction, Bruno. Can you hear me at the back? Okay, great. If you can't, make a wave. So this lecture is a primer, which means I assume you don't know anything about vision in language. But one thing I've realized over the last couple of days is that many of you know a lot more than I do. So I hope this will still be useful for some of you. The slides are already available online. So if you want to annotate them on your iPad or some kind of computer, feel free to do that as we go along. This was probably the most difficult slide for me to make. I really struggled to find a working definition of what it means to be vision and language learning. And so I actually abstracted a bit to this idea of multimodal learning. And in multimodal learning, we're mostly interested in processing joint representations of inputs from one or more or two or more modalities. So for example, images and text, or perhaps speech and video, or maybe video and text. And so if you're familiar with this famous XKCD, I've now adapted it so that instead of having just one funnel for data, we have many. And we really hope that what happens when we stir this around will be better than having just one input modality. You may ask, okay, I understand your definition, but why do I care about this? Well, there's a long established tradition of research in neuroscience, which shows that humans do ground conceptual knowledge in modality processing systems in the brain, and that there's some evidence that similar parts of the brain are activated when they are dealing with different inputs, but ultimately concerning the same topic. This example here shows an fMRI scan, and on your left-hand side, this is when someone is actually moving that part of their body. So the blue regions are the feet and the red regions are the fingers. And on the right-hand side, it's when a person is sitting in an MRI scanner, but they are reading words concerning those parts of the body. And we can see that there are some co-activations suggesting that the brain is grounding these through some similar pathways. And from a more kind of pragmatic perspective, multimodality can help to reduce ambiguity. This sentence here is ambiguous in isolation. And if you were a state-of-the-art robot, you may be confused about what the instruction is. But if you see this in context, then you can use your eyes to recognize that there are cigarette butts littered on top and around this bin. And that if you were to stick your physical butt there, it would be really unpleasant. And this is the type of ambiguity that's difficult to resolve from text-only inputs. There's also a very well-known claim of the things you cannot learn language from. In 2020, there was an interesting paper on experience grounding language, where if we start from the innermost circle, where we have text corpora that we carefully create, as you step outwards from this circle, there are different things that you cannot really learn language from. at least this is the claim, that you cannot learn about language from the radio without grounding because you lack perception. You cannot learn language from the television because you don't interact with the television. And this is because you lack embodiment. In other words, you're just a passive agent. And you cannot learn language without interacting with other people because you lack some kind of social context in which language is a medium of communicative exchange, which is, I think, how it has been argued to have developed over the history of humankind. And so if we continue to focus our efforts on learning about language from text corpora or the whole internet, we may reach eventual problems. I'll actually argue against this later in my talk, but that's okay. It can be inconsistent. There are at least 5 major areas of research in vision and language, and we're going to try and cover different parts of this today. This survey from 2018 covers these 5 topics: representation, translation, alignment, fusion, and co-learning. And I think this can be a useful framework for thinking about different problems that we'll discuss today and that perhaps you'll think about later during your research. If we start from this idea of representation, there's been a huge amount of work on this over the last decade or 20 or 30 years, going from things like histogram of oriented gradient features, like the thing shown here on the left, which was a really cool thing, really exciting representation format at the time in 2005, to the early 2020s, where we have clip features and you just throw your dog into a vision transformer and you get a single vector. In terms of translation, there has been an explosion of work on end-to-end neural networks since the mid-2010s. Very shortly after the paper on sequence-to-sequence learning, there was a paper showing how to generate sentences from ConvNet representations of images. So these were projects that you can presume happened simultaneously within a mind. And now in 2022, we have these stable diffusion-based models where we can generate or attempt to generate images of almost anything we can write down in a prompt and refine over time. In this case, we're translating from an image to a sentence, a cross-modal translation, or the reverse in the other direction. There's also this key problem of alignment. How do I know that 2 things mean the same thing? So you can take this from the perspective of like a common metric learning problem, maybe where you have multiple instances and you want to match your true instance in one modality to its pair in another modality. You can also think about this at a more fine-grained level. Maybe you want to take an image and ground a particular phrase into where that's located in the image. So this is an example of the MDETR model, grounding directly into the pink shaded elephant and not being confused by the other elephants that are located in the image. In terms of fusion, early work studied the differences between what we call early fusion and late fusion. And so on the right-hand side at the top here, we have this kind of late fusion model where we'd have 2 different towers that would independently process features in different modalities. And then maybe we would combine these together with a concat function and have a simple linear layer. What we have now with multi-head self-attention is model-based fusion. It happens through every layer in the model after the input, and it learns these rich contextualized representations, which have proven to be very useful for many tasks. Co-learning is one of these areas that we don't see much of, but it's really exciting, this idea of doing a zero-shot transfer across modalities, where maybe you learn some kind of manifold of object or image labels, and you can use this to do zero-shot transfer for images you've never seen before with classes you don't necessarily know. In this case, the label space can be initialized from some kind of pre-trained space. Or there's this idea of trying to use visual supervision to improve language processing models from 2020, where they would try to visualize which words could be aligned with, which images could be aligned with particular words in an input. I'm not going to spend the next 3 hours talking about all of those 5 things directly. Instead, I'm prepared a roadmap. So we're going to try and work through the entire life cycle of doing multimodal research. I'll start by talking about some of the important issues and data sets in this area, and it's become a bit more of a controversial issue in recent times with the arrival of generative text-to-image models. I'll speak about some of our work that's related to data set creation. I'll also talk more about data representation in terms of how you actually process vision and language data if you want to do this yourself. I'll speak about some work on modeling techniques. We're mostly focused on things like multimodal transformers. And I'll also talk about some work we've done there on retrieval augmentation and how useful that should be in the future for multimodal modeling. Then I'll talk about some work that people have been doing on trying to understand multimodal models to probe their strengths and weaknesses. And finally, I'll speculate about what I think are some interesting directions for future research in this area and talk about some of our recent work that Bruno mentioned in his kind introduction, where I think that maybe language and vision could be the same thing. So without further ado, a multimodal data set is typically either crowdsourced or it's harvested from the web using massive Python scripts and huge data servers. It typically consists of 2 or 3 parts. So we'll have some kind of non-linguistic stimuli, like this image of a cat, or maybe a video or some kind of, well, speech would be a linguistic stimuli. And then we'll have a linguistic stimuli. In this case, it's a question. What color is the cat's leash? And there's an optional additional piece of input here, which would be a task label. Not all multimodal data sets have these types of downstream tasks associated with them. So this is the kind of the common framework we'll think about when we are thinking about multimodal data sets. And there are 2 main types here. There are general purpose data sets where you have visual data with descriptive annotations. These are typically large scale. They are scraped from the web. Some examples that you may have heard of would be things like conceptual captions, or maybe the Lion dataset, or maybe something like the Speech Coco dataset. And so we have an example here. This is an actual example from Lion, where they have, I guess, an image from maybe an e-commerce website and a description of what that e-commerce website object looks like. And then you can also have task-specific data sets where we usually have something like classification labels or something similar. This could be for something like video captioning or visual question answering, or maybe some kind of visually grounded reasoning task. In this case, there will usually be some kind of descriptive annotation, like maybe a question or a statement expressed in text. But there's also this idea of trying to do an additional task. Something I often like to think about, but I've never really got around to formalizing, is that there's this idea of a degree of multimodality between a non-linguistic and a linguistic stimuli. I took this photograph from the internet yesterday, and you can imagine if we were to crowdsource this, we asked people on the internet to describe this in a short and simple sentence, they might write something like what you see on the right-hand side. And I call this strong multimodality because you can imagine it's quite easy for a model to bind different parts of the text into different parts of the image. It can recognize the person as being a woman. It may also be able to recognize the clothes that she's wearing. And it may be able to ground this idea of giving a speech into the lectern and also the microphones above that. The actual caption that appears with this image is the thing on the left-hand side, which it's very difficult to imagine grounding this into the image. This is more of a societal level, contextual description of what's happening. And that's often the case in news media. And this also reminds me of some seminal work by Erwin Panofsky in his studies of iconology, where he argues that there are different levels at which you can interpret paintings. And I know this isn't a painting, but if you'll allow me the time to extrapolate, I'm sure you'll see that the example on the right-hand side really requires no knowledge of the world beyond simple everyday life. It doesn't even say who the woman is. Whereas to actually explain who this is and maybe what she's talking about, you need rich understanding maybe of German politics or European politics and the particular news issues of the day. So I'm going to talk now through some of the most common data sets and explain some of their properties and maybe some of the interesting tricks that have gone along the way. The conceptual captions dataset was created by Google Research, and it's typically used for pre-training. There are two versions. There's one which has 3 million images and one which has 12 million images. We used to think these were really huge data sets, but now they're tiny. They are associated with normalized image captions. And so the pipeline is shown here on the right-hand side. So they start off by taking a huge collection of image URLs, which are associated with alt texts. And if you're a company like Google, it's probably not difficult to find a large collection of images with alt texts. What they do from here is they have stages where they do text filtering and image filtering, and then they also have a transformation on the text, where you might take some of the proper nouns in the text, like people's names or places, and convert these into kind of more straightforward language. So on the left-hand side, if you maybe can't see this, it says Demi Lovato wearing a black Esther Abner spring 2018 gown. And after the text normalization on the right-hand side, we have pop rock artist wearing a black gown. It's easier to see that the example on the left-hand side is maybe this kind of weak multimodality. It's difficult to imagine grounding this into the image, whereas the example on the right-hand side is much more strong multimodal relationship. It's easier to bind the text to the image data. The normalization process is not publicly available. We have tried to reproduce parts of this. It turns out it's really hard to do this with open source tools. In the original paper, they describe that they use Google internal tools and the Google Text API. We were unable to successfully reproduce this using tools like Spacey. And due to link rot, there are probably fewer images available online now. It used to be 3.3 million. When we harvested them, I think in 2019, it was maybe 2.9 million. It will be much less now. So yeah, you should have downloaded them in 2018, I think is the main conclusion. And this is due to issues with distributing the images. So they distribute the URLs. The Lion dataset is like this conceptual captions idea, but with scale. This is also used for pre-training, and they start with Common Crawl as their initial point. Common Crawl is enormous. I think if you want to get a copy of Common Crawl, you need to pay to have hard disks delivered to you. It's huge. And from there, they have different filtering techniques that are used based on the content of the pages or maybe the actual image data or text data. And they use this to store huge amounts of data. So they have a 400 million version, a 2 billion version. Both of those are in English, and then a 5 billion version, which is multilingual. And we can see some of the, like this is an example here. I don't speak this language, so I can't even explain what this might be. Does someone here speak this language? Nope. Okay. So yeah, it's obviously e-commerce images. It's much larger scale. And it's the data behind some of these models you've heard of, like Stable Diffusion and OpenClip. The COCO dataset is both a general purpose and a task-specific dataset. So it can be used for pre-training. It's quite small in scale, but the captions are really rich descriptions with strong multimodality here. They were crowdsourced from the internet, and the images cover 80 common types of objects in a context. And the captions are shown over here. There are also segmentation masks where almost every sheet is annotated. That's great fun. And this is something that you can use for computer vision only tasks or multimodal tasks, depending on your interests. Something like VQA is where we have a much more task-centric data set. And the goal here is to answer questions about images. And so you typically have like this example here on the right-hand side. The question might be who is wearing glasses? Over time, these data sets have developed to avoid kind of shortcuts or simple biases that can be learned from the data. So we'll end up having evaluation sets where the model really has to understand the person that's wearing the object rather than just extracting the most likely answer from the training set. And the evaluation set is, I think, very well balanced in this perspective. It's commonly tackled as a classification task over a discrete output space, but there are increasing efforts now to view this as a natural language generation task. And this is as a result of some of the most state-of-the-art vision and language models. There are over 1 million training examples here, so it's a large-scale data collection effort. There are also negative answers that have been sampled that could be plausible. So this seems to be some kind of useful learning signal along the way. NLVR is a different type of task. It's more kind of about visual reasoning, where it's a binary classification problem. And what you would like to do here is to determine whether the sentence is a valid statement about the pair of images. The rationale for this is that a model would need to actually understand both images and the sentence in context in order to make a more than trivial progress in this area. And the hard negatives were created by humans. They weren't sampled automatically from the data. Visual common sense reasoning is a case where we go beyond what we have been thinking about already. Maybe Yejin spoke about this a couple of days ago. I was flying, so I didn't see her talk. But this is a piece of work from her research group in Seattle, where we now have these kind of multiple choice VQA problems, and the examples are derived from movies. And in addition to this kind of question answering problem, we also have to a setting where models can produce rationales. So it's not just a case of trying to figure out the correct answer given the image. You also have to try and explain why. And maybe the image is too low resolution here. But this is a really interesting challenge that goes beyond what you can just learn by looking at an image. You have to reason a bit more deeply. One thing that's been missing from our discussion so far this morning is, why is everything English? This has been an ongoing issue in the multimodality field. In 2016, there was an effort to create multilingual multimodal data, which is aligned at the image sentence level. And so far, this effort has resulted in data sets in English and German and French and Czech and Arabic and Turkish and Japanese and most recently Ukrainian. The images, it's quite a small image data set of only 30,000 images, but at least in the English and the Japanese data, there's fine-grained alignments between parts of the sentence and parts of the image, so you can determine whether your models are actually processing what you expect. There's also some completely different perspectives on multimodal learning here, which is much more interesting from a linguistic perspective. There are many data sets on sign language processing. I think that video probably only ran once. This example from the University of Oxford shows where they have videos where they've extracted a signed speaker from BBC broadcasts. And this can be used to work on things like sign spotting or sentence localization, or even just sign to text translation tasks. And in this case, there's 1,400 hours of signed shows, which is a lot of data. I know that you need to sign, I think, a special license in order to use this, like you won't use it to create commercial products. And there are many different directions in this area. So there's a large-scale German data set. I know there's a data set associated with YouTube videos as well. And so if you're maybe interested in things like sign language processing, then this is a nice place to get started in that direction. That's playing the video. And there are many, 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 many more data sets and tasks and problems in this area. And I could have spent 3 hours talking about this, but we will have to move on. This is just a short list of what you could see out there. Maybe you're interested in things like vision and language navigation for people like Johnny 5 or automated mobiles. Maybe you're interested in things like abstract reasoning. So that could be things like the kilogram dataset from EMNLP last year. Maybe you're interested in visual storytelling, so working with sequences of images that are not necessarily videos, but instead they tell a story as a collection. And so now I would like to transition to telling, oh, I lied. There are many arising ethical issues in this area. So multimodal datasets are usually scraped from the web with unknown or unspecified degrees of conformance about licensing. Maybe all of you know about Creative Commons. Creative Commons licenses are available in many different formats, and they are irrevocable licenses. And as of 2022, according to Creative Commons Foundation, there are about 2.5 billion Creative Commons licensed objects. And that's not just images or videos, it's also things like digital objects, like data sets. It could also be web pages, like Wikipedia would be an example of this. And so one thing I often think about is, could people have been reasonably expected to imagine that distribute or build upon would include harvest and use for large-scale machine learning research in corporations? I'm not sure. I think I used to have a Flickr account and I uploaded some images there using Creative Commons licenses, and I never imagined a future in which this would have happened. And maybe that's because I lack the ability to foresee mega machines coming on the horizon. Another thing that occurs to me is that there's this big problem with scale where, so Birhein has this really exciting paper from 2021 that when you build these really large scale systems trained on web scale data, they tend to perpetuate harmful stereotypes. And so we have an example here of Eileen Collins, the American astronaut. And if you use the CLIP model and you try to determine the similarity of the first statement with the image, it's actually less similar than the second statement, which describes the person in the image in a completely incorrect format. And so this is something that I think we should be aware of as we think about scaling up systems, that we shouldn't want to perpetuate these types of stereotypes. And that the pre-2022 web, we have to think about what we're going to see in our reflection in the future. This could be the last large-scale source of non-AI generated multimodal data. And I think we should maybe consider some of the the consequences of that, of learning from generated images or automatically generated videos. Are we going to be happy with what happens when we keep training on this data? I know some people have looked at this from a text-only perspective of what happens if you keep training on generated examples. We tried to do something like this in my group, where we tried to train image captioning models with Stable Diffusion generated data. And the scary thing is it actually improved performance a little bit. And the images it generated were truly terrifying. They're not human beings, really, things with 3 legs, bicycles that are completely physically implausible. But it worked. And it's kind of concerning. It should cause us some thought in the future. And so now I'd like to maybe reflect on, like, how can we collect multimodal data that better reflects the diversity of the world? As I've said already, most of the data sets I've been talking about are English language data sets. They are Western centric. And so in 2021, we had what I thought was a really exciting project to create visually grounded reasoning data across different languages and cultures. And this was a project jointly led by Fang Yu and Emanuele. And so the typical vision and language data, you already know this slide. You already know what the core data sets are out there. So we have things like ImageNet or COCO. ImageNet is derived from the English WordNet hierarchy, whereas something like COCO are these images with these 80 commonly occurring objects. And derived from the WordNet hierarchy and these commonly occurring objects should already maybe set some alarms ringing about which types of images we can expect to find here. And so what we tried to do in this direction was to rethink the data that we were using. Even if you work with non-native speakers of English or native speakers of different languages, you can get weird artifacts. For those of you that understand or speak Dutch, or you've spent a lot of time in the Netherlands, you would know that this vehicle is a draaiorgel. This is just obvious to you because you've seen them all of your life. Whereas if you ask crowd workers who speak English and maybe live in the United States, they call this an unusual looking vehicle. And you can imagine what will happen in the reverse direction if you collect data representing different cultures and you ask English speakers living in Northern Europe or the United States to describe them. And part of this is because the sources of image data that people typically work with reflect North American or European cultures. This density map of geographic distribution for ImageNet shows basically that. There's very little data coming from South America, Australasia, Africa, or Asia. And so this, I think, has really important implications for vision and language research. We end up having narrow linguistic or cultural domains, and there's no real way to assess how they'll perform in real-world situations. If we think back to when we learned about concepts and hierarchies of concepts, then, I mean, the idea here is that you would have some kind of concept of dog as a kind of mental concept in your mind, and it could be realized through some kind of category representation. For example, here, these 2 cute dogs. And the categories form a hierarchy, and this has been some of the basis for work like WordNet. And it's also known that people are very good at using things like basic level categories when they struggle to express things in a more concise way. We saw this on the previous slide. It was an unusual looking vehicle. They didn't try to describe what the vehicle was. They just said it was unusual. And that these concepts are somewhat universal, but there are different relationships through different cultures. And there's also familiarity of individuals playing a huge role here. And so we can maybe take some kind of definition here to say that culture is the way of life of a collection of people that distinguishes them from others. And that some concepts are most immediately understood within these types of cultural backgrounds. I have 3 images to test you. Does anybody know what the image on the left represents? It's not a trick question. You'll either know it or you won't. It is, yes, pilota or jai alai. Does anybody know about the concept represented in the middle image? I think somebody almost said the word, but I couldn't hear you. I think somebody's saying shamisen. Yes, although I once spoke about this and some people said, no, this is Asanshan, and I got really confused. So maybe it can be both of these. But I don't have the cultural background to understand the difference between those. And for the one on the right-hand side, I would be very surprised if any of you knew this. So this is called a clavey. This is something that happens 6 miles from my hometown. It's an ancient tradition where we fill a barrel of tar and set it on fire and carry it around the streets to celebrate the new year, like you do. So yeah, and you can imagine that if you asked people to describe these different visual concepts, they might say something like sport or music or fire. And so one thing you can ask is, are ImageNet concepts actually cross-lingual? So we do this by taking the labels of objects in ImageNet and then looking at Wikipedia as a proxy for this. So you take some kind of concept or synset in ImageNet from English, and you look to see, are there links to other languages? That means that the page exists there. Someone thought it was worthwhile describing this in an article in a crowdsourced endeavor. And what we find here, where the y-axis shows counts and the x-axis shows the number of languages per synset, most concepts appear in 30 or fewer languages. And there are very few universal concepts as represented through Wikipedia. And I know that Wikipedia is not the ground truth of conceptual representation across humanity, but it suggests that there's something missing here. And so what we did was to introduce this resource that we call Marvel, where the images are representative of annotators' different cultures, and the text is from 5 typologically diverse languages where we have independent and culture-specific annotations. This is an example of the concept for basketball across these 5 languages. And so we have Indonesian, Swahili, Turkish, Chinese, and Tamil. One thing you can see here from the basketball example is that basketball looks pretty uniform across languages. There are people in courts and nets. They're all wearing long, baggy shorts. So there are some things here that we can find in common. And how do you collect this type of data? With a lot of time. So we have a native speaker-driven protocol where we have these 3 stages. There's concept selection, image selection, and then annotation. And so it's a visual reasoning task, like I mentioned earlier. So we have a data point where we have 2 images paired with a sentence. The sentence does not exist in any language apart from the source language. So if you don't read Tamil, I'm sorry. But I think it says something about how many people are engaged in bull taming in one image compared to the other. So this is one of our data points. The images were crowdsourced, the sentence was crowdsourced, and the task a model has to perform is to predict whether the sentence is a true description of the pair of images or not. And I believe that this image represents some kind of religious festival. It's not just a case of people fighting with an animal. And so Marvel is created from universal concepts. We took this from the Intercontinental Dictionary series, and we focus on the chapters that have concrete objects or events. So we're interested in images that maybe have things like animals or food or things to do with the house, or maybe things to do with celebrations or important religious events. We don't have much focus on the more abstract concepts that are not easily grounded. And this is where we introduce a bias into the data set. So this is something that's very difficult to avoid. You always have to make a decision when you're making these types of resources. And so in step one, we ask our native speakers to give us a list of concepts that should be representative of their culture, and they are ideally either physical or concrete. And so maybe the person is prompted with the semantic field from the ICD, like sport, and then they go to Wikipedia and they find examples of articles that describe this sport activity. And from there, we take the top 5 per each semantic field across our native speakers. And we end up with about 90 concepts per language from this process. And one of the things that we see is that in most of the cases, between 15 to 25% of these concepts just don't seem to exist anywhere in the WordNet hierarchy. So if you do your research starting from somewhere like WordNet, you won't be able to imagine that you can process this type of data well. The second step is based on image collection, which we also do with native speakers. And our images are collected such that they contain more than one instance of a concept, perhaps the concept is interacting with other objects where it's relevant, that if relevant, it shows an instance of that concept being used in an activity, or that it maybe displays a diverse set of objects in some kind of grounded context. So it's not just an example of a shovel in a kind of e-commerce website, or it's not just buttermilk in a carton. It's showing a lot more than what's going on there. And then for the language annotation step, this is also written by native speakers. We pair 4 images from the same concept in a language at random. And then our native speaker workers write a caption that's true for only 2 pairs. And so they write this caption. And then we have another native speaker set where they validate the annotations to say whether this is indeed a correct representation. And this is, if it isn't the case, we go back and collect more data. And then we end up with a final validation where we have a data set and we have images like this. And you have sentences where the gloss would say that the man in the right image is serving a ball while the man in the left image is returning a ball. And this is something that we hope requires a kind of fine-grained vision and language understanding, not in English, but in this case, in Chinese. And the inter-annotator agreement for this final validation phase is very high. So it's quite a reliable process at the end. So we have some examples here to show you what they might look like. This is an example from our Turkish data. So the gloss for this is that in one of the images, there are multiple people with kanuns on their knees. The label here is true. This instrument is shown here on the right-hand side. And in the second example here, we have a concept for this thing called a masala vada. And I'm told that it's false because only the image on the left contains masala vada, or maybe it's only the image on the right. Does anyone know the answer to this? Nope. That's the masala vada. And the one on the right is something different. Yeah, see, even though I've spoken about this a few times, I still don't have the cultural context to remember this stuff. It's not part of my daily experience. And so we end up with 5,500 data points across 5 languages. And the main takeaway here is that this data covers many more language families than taking only English examples scraped from things like Coco or ImageNet. And once we have this data, we can train and evaluate models on it to see how well they actually understand these cross-cultural concepts. So we have 2 models that we evaluate here. They're pre-trained in a combination of the English conceptual captions data, which we've already discussed, and 104 languages version of Wikipedia. One model is initialized from MBERT, the other from XLM Roberta. And then after pre-training, we fine-tune on only the English data. And then we want to see how well we can do cross-lingual transfer in a 0-shot setting. Does the model actually understand the concepts in the images and the text, or is it somehow just faking it? We can also do a translate test version of this where we translate maybe from Tamil into English. the results are unsurprisingly much stronger there. And so, yes, as a sanity check, we find that the two models that we pre-train on the right-hand side perform similarly well to models for vision and language at the same time. Don't worry that you don't know what these are. We'll come back to that in about 3 parts of the talk, of the lecture. So what we find is that these models perform similarly, everything is okay. And then when we try to do zero-shot transfer, the performance for English, as I'm copied over from the last slide, is quite good. The performance in other languages in a zero-shot setting is almost random. There's no evidence that it can do any cross-lingual transfer in this kind of visually grounded setting. And that's consistent across almost all of the languages here. Our best performance is 57 accuracy. And so, I missed a slide. When you do translation here, the performance improves a lot, suggesting that if the model could process the data in English, then it's able to do some kind of binding. And that maybe the problem is it's unable to bind these tokens, that it's never actually seen in a visually grounded context. It's only seen them in a text-only Wikipedia context. And so what I'd want to conclude from this first part of the lecture is that there are many existing data sets in vision and language that have a North American or EU-based bias. And I've discussed how we can maybe devise a new type of protocol for creating data, which is driven entirely by native speakers. We create this data set called Marvel, which is for vision and language reasoning in these 5 typologically diverse languages. I should have said all of our data was collected from images under a Creative Commons license. I think there are also implications for these ideas beyond vision and language research. I think that other people have started to follow this direction as well, that multilingual data sets should not just be translations of English data. It's not enough to say that we can do processing in Portuguese if we're just doing processing of English sentences that are translated into Portuguese. We're not having to really understand the concepts of Portuguese life. Like yesterday, I went out for dinner and I had this thing called a goose barnacle, which was quite terrifying at first. But it was really tasty in the end. But when I was presented with this, I had no concept of how to think about this. And I think if I had a data set of sentences in Portuguese that I translated from English, this concept might never appear. So I guess now is a good time to stop and take some questions people might have about dataset creation or maybe cross-lingual or cross-cultural learning.
Hi, can you hear me? Yeah. I was just wondering where you see the role of data sets that have been created using, say, an embodied simulator. I'm just thinking of data sets like SimVQA and those kind of more, I suppose, somewhat abstracted, but more systematic ways of creating these kind of data sets. Yeah, what's your take on that?
I think it's a really exciting direction for research. And it's one that I've often wanted to get involved in myself, but I feel like the idea of also having to get involved with artificial agents in reinforcement learning settings, if I understand the data sets you're talking about correctly. No?
So those are static ones. They are not actually, they don't require any interaction. They just take stills essentially of they just use it to have some form of way to systematically create scenes.
So this could be things like
Clever
was an example of this, where they have these images where they have these different spheres or cubes and they're colored in different textures. Is that kind of direction?
But this time with actual objects. Yeah, I think it's quite exciting. So I was wondering if you've come across it.
I haven't come across that, but thanks for mentioning it. That sounds really interesting. And you could use that to do really controlled experiments on things like, does my model understand this composition of concepts? We've done some work on that in the past. We find that models really struggle to understand novel compositions. So if there are synthetic data sets where we can evaluate that more carefully, that sounds super cool. Thanks. I can hear you.
Very clear. You talked about building your proposal figure. You didn't expect that you would train any kind of so, and so you talked about Creative Commons, but what about the GDPR? Right, like in the beginning, you showed us when you talked about PQA, we showed pictures of people, of child. I'm not sure they want to be like, yeah.
Sorry. Yeah, so the question was about GDPR issues and the role that that plays in multimodal data. Yeah, this is a really important topic, and it's not often discussed. The GDPR has a very long arm. It reaches everywhere. I think it could probably reach the moon if it was necessary. And I do agree that people have the right to not have their personal information processed by random people around the world. I know that there's a recent data set from Meta for their Segment Everything project, where I think all of the faces are blurred. So I imagine that this is an attempt to adhere to the GDPR, but we also know that I think you can predict who people are from their expected contexts. So maybe it doesn't go far enough. I mean, I think that there are many challenges here. It's something that causes me real difficulties in the research we're doing. So when I want to create new data sets like this, I need to speak to the data protection officer, or not. It's very difficult. And so you can understand how companies will say, we won't distribute any images, we'll just give you URLs. And if you break the GDPR, then that's on you. None of these are good answers to your question. It's very complex. And there's also the new EU AI Act. I'm not sure exactly how this will interact with all of these different issues. I don't have a good answer. It's a good question. I think we have maybe one question here at the front. Maybe the mic isn't even working.
So my question is about the process of creating the data set and the annotation guidelines.
Mm-hmm.
So I understand that we, of course, don't want this American view of the world, but at the same time, by seeing like the 3 pictures that you showed before, like the Basque and the fire, I forgot the name already, sorry. But I was wondering like how well is this when you actually train the data set? Because I wonder that if it saw more images of fire, how would you know if it's actually this cultural festival or if it's just a normal fire? So, and yeah, so I was just wondering because I would believe that this happens a lot. And you were talking before about the degree of, what is it, the multimodality. So isn't that going more like to the weak description that you showed? Like what are the boundaries between actually being having a strong degree and also respecting the cultural biases?
Thanks for the question. So we don't fully understand the extent to which these models correctly process the type of multilingual and multimodal data. We can do some kind of post hoc analyses where we translate the data into different languages to see what happens there. We can also have humans perform some of the processing themselves using native speakers, so we get deeper insights into what's happening. So I think that there are many issues in that direction that we haven't yet resolved. With regards to your question about the degree of multimodality, I think this is perhaps why I've never written anything formal about this. To me, it's a very kind of loose concept in my mind. It's not fully fleshed out. I think that some of these examples, like in one of the images, there are multiple people with cannons on their knees. I think this is quite it's quite easy to bind some of the words into the image. If you know what the Turkish word is associated with people, and you know what the Turkish word is for kanun and the part of the body, I think this should be quite easy if the model can actually do it. And when we translate this Turkish example into English using machine translation, its performance is much better. So one thing that we know is that there is some kind of binding issue in the multilingual data, which is quite frustrating from a modeling perspective, because we would like to think that our cross-lingual model really can do this type of zero-shot learning. One of the things we've seen in some of the talks is this push towards zero-shot transfer for natural language processing tasks in general. And if we're failing at this stage, I wonder how much further we'll have to go. But did I actually answer your question? I got lost. Very generous of you. Thank you. Okay. It's 10:02 and we'll keep going. So the second part is going to be about data representation. This is like, okay, my supervisor has asked me to work on this multimodal project, and I'd rather not, but I need to do something. So I need to understand how I'm actually going to get this done. I like to think of there as being three levels of representation. There's perceptual representation, there's working with pre-processed features, or there's working with raw inputs directly. And perceptual representation is an older idea that has lost some fashion, but it's still good fun, and there's quite a lot you can learn from this. So this is the idea that you might ask people to write down a list of words that are triggered by some kind of concrete textual stimulus. So this is an example from McRae and colleagues, where the stimulus is moose, and then people have to write down the list of words that they associate with this, or the list of phrases. We could have done this together here today, and I could have hidden this and see if you agree with the people that he worked with. So yeah, a moose is large, it has antlers, it has legs. You can view this kind of as a description of some kind of mental image that you have in your mind. And one thing that's also really nice about this type of idea of working with perceptual norms is that you can categorize the source of the knowledge. So if you also have human annotators, you can say, well, the fact that a moose has antlers is to do with its visual form. Or you can say, if there were things like moose is hunted by people, this is kind of a functional aspect of a moose. Or maybe there's some kind of taxonomic relationship, like it's a herbivore. There has been some really interesting research on using these types of perceptual norms as inputs that represent visual data instead of using visual data directly. And most of that work happened before the deep learning revolution, where we had convnets that could just represent our data as dense vectors. And so if I had to summarize the pros and cons of using perceptual norms, you can end up having some really rich and interesting features from this. But some of the cons, is it actually going to scale up when you want to collect more perceptual norms? I'm not convinced. And also, how do you handle ambiguity where people might think you mean a different instantiation of a particular concept? And at a more general level, what does it mean for our models to only understand symbols as defined by other symbols? I'm not the first person to ask this question. This goes back to philosophers like Searle. thinking about the Chinese room argument and what does this actually mean about some kind of computer that would operationalize this translation system. And so we can then jump forwards. We're going to go straight past the sift and hog feature era. Now we are working with convolutional neural nets, or maybe some kind of other representation of through a neural net. And here people typically use things like pooled features or spatial features. So you imagine here you have your image of a car, you have this represented 224 by 224 by RGB3, and then you have a series of conv layers with max pooling layers in between, so that you downsample along the way whilst increasing the feature depth through the model. And then if you're working with something like pooled features and you're reading a paper, you'll see something like this. CNN of IB transforms the pixels inside the bounding box into a 4096 dimensional activations of the fully connected layer immediately before the classifier. This is what you're looking for when people say, I'm using a convnet with pooled features. It's that part, it's that kind of phrasing. If you're thinking, if it's a paper that's using spatial features, you're going to find something like, in our experiments, we use the 14 by 14 by 512 feature map of the fourth convolutional layer before max pooling. And you would read papers at this time and you'd be like, okay, you used the fourth layer, I used the fifth layer, doesn't matter, I don't know, let's just keep trying. And so this would typically be the layer before this dense layer, and then eventually the dense layer was just replaced with an average pooling. And so some of this knowledge doesn't transfer directly. But if you go back and read some of these papers, this is how it's going to be expressed. There's also a push towards this idea of using pre-processed visual features from regions. And you typically have an input image down here at the bottom, and it goes through a convolutional layer. A region proposal network suggests where there may be regions of interest, where there might be things like objects or stuff. And then there's a pooling layer, which you can take a spatial pooling over this to get a dense vector that represents just that region of interest in the image, not necessarily the surrounding context. And this was a very successful approach that was first used in this direction by Anderson and colleagues to substantially improve captioning in VQA systems. If you're reading a paper that does this, you'll see something like this. Our models are trained with 36 regions of interest extracted by a faster RCNN with a ResNet 101 backbone. Awesome. So these are going to be where the regions of interest are coming from. It's this proposal network. And this ResNet backbone is this thing down here at the bottom. This is usually trained on something called the visual genome dataset, which we haven't discussed, but you can imagine this as being a dataset with richly annotated relationships between parts of the image. So if I had to sum up some pros and cons of this, I would say one of the major pros is this is a very long established practice, and it's usually offline. So you do it once, you pray that you did it as they described in the paper you're trying to reproduce. Install all the wrong versions of CUDA along the way, and then you forget about it. You just store it in this kind of, which is a con, some kind of specialized storage container like H5FS. You have to split it into many different containers and figure out how to index them just in time. It's not obvious how to do good random augmentations in this format because you've already processed the data, and then you just be randomly augmenting the visual features that come out of that instead of doing augmentations in the original RGB image space. And this type of specialist knowledge can be quite opaque to newcomers. That's why I've given you some examples of how this will be written in a paper so that you're equipped to become experts in this yourself. In terms of raw input, this is now the direction that we're really starting to see where for images, we'll process this using something like a vision transformer or a SWIN transformer, or for speech, you could use something like a spectrogram transformer or the audio MAE. And you're already experts in how the vision transformer works because you had a lecture on transformers. The way that it actually works is you take an image and you split it into K patches where the patches are similarly sized. You embed each patch, you add position information. You already know all of this. You're all experts in embedding and position embeddings. And then the transformer block has one difference. There's an extra prenorm layer that's put there for stability. And this is something that you also see in some of the more recent GPT-based models. It makes training much more stable and reliable. So now we've gone from, we're going to describe images in terms of words to, I'm going to split an image into equally sized patches and just use a transformer. And so when you're working with transformers, there's some really weird nomenclature. I'm just going to quickly cover this because it didn't make sense to me at the start, but if you already know this, then awesome. So you'll see stuff like this. We use VIT B32384, and you're like, come on. So the first part is going to be the model family. This will usually be something like VIT or SWIN or LIT. The B is going to be the model size, or the size of the transformer. The third part is going to be the patch size. So when I said you split it into K patches, it's K by K pixels. And then the last part is going to be the input size of the image that the vision transformer processed. Some image sizes and patch sizes are not compatible because they don't give you whole numbers. And there's an important point here, which is that the number of patch embeddings is a function of the image size and the patch size. And we're working with transformers and we have self-attention, and it's typically a quadratic operation. So if you're working with something like VIT base, 32 pixels per patch, 384 by 384, you have 144 additional inputs to your transformer. And that's a lot of extra GPU RAM. If you're using something like a huge VIT model, which is already billions and billions of parameters, and you're using 14 by 14 patches, and your image is 448 pixels, you have so much you need here. This is like 1,000 patches of input just to process your image. You'd have to ask yourself whether you actually need that kind of resolution of information. Maybe if you're doing medical image processing, it makes a lot of sense. If you're trying to determine which person is wearing glasses in a photograph, maybe it's not necessary. Although you could squeeze out a little bit of extra performance if that matters to you. And the way that these types of features are extracted, well, you're already experts in transformers, so you know how to do most of this already. So when we're taking pooled features, we'll see something like this. To extract visual information from an image, we use the visual encoder of a pre-trained clip model. No other information in that sentence. Whereas if we're going to use patch level features, they'll say something like, we extract the feature grid before the pooling layers, resulting in an n by n grid, where we have 7 by 7 or 12 for these differently sized models within the clip family of models. And so then we'll get this one output embedding per patch. And that will be our representations of our inputs. So if I had to summarize some of the pros and cons here, one of the big pros is that data augmentation is now straightforward because you're working directly from the raw input. You're reading the images from an arrow file or from a disk. There are fewer pre-processing steps, which means you have fewer creeping errors, like you installed the wrong version of faster RCNN and you wasted 2 weeks extracting visual features. Some of the cons are that you're now going to be able, you're only going to be able to work with smaller batches because you'll typically have an extra model on your GPU. So now if you've got something like Roberta large and you put a VIT large model on there as well, that's a lot of extra information you need to store. And like I just tried to highlight, you can have potentially many, many inputs. And this is something you can control. But it's something you should be aware of while thinking about that. Okay, so in summary, I think here there are many options for how you'd like to represent your multimodal inputs. They can be language oriented, they can be objects or stuff oriented, or you can work directly from raw inputs. I think there's probably no universally best option, but the raw inputs are promising, in my opinion, because the visual representation model can be fully differentiable. And we've already seen from all of our lectures on NLP that full differentiability is a really important path to success. So the next part, which I will briefly start, and then we'll have a quick coffee break, is about modeling. So there are two main approaches to modeling in my mind. There are cross-encoding models, also known as multimodal transformers or vision and language BERTs. And there are dual encoding models. For example, a dual tower model that you see on the right-hand side, where you would independently process language or vision data, and then maybe combine them at the end. So the thing on the left-hand side, you can see as being a model-based fusion. Everything is being fused at every layer in the model. And on the right-hand side, we have this late fusion that I spoke about at the start of this morning's lecture, where we'll process the red horse separately from vision, and then maybe we'll just measure something like the dot product similarity between the vectors. Or if we have a task, then we might fuse these vectors together and then do some kind of later processing on that. I just realized that I've been told we would take a photograph, and maybe it's beneficial for us to end a little bit earlier so we can fit that in. We're okay? We're okay. So I'm going to dive into both of these approaches. So for the cross-encoding models, these emerged as a key approach in 2019 with a flurry of models on creating visually grounded BERT models. As I said before, it's a form of model-based fusion, and the backbone consists usually of a language model and a visual encoder. And a really high-level overview of how this works is that you typically have some kind of representation of the image. It could be object representations, maybe extracted from faster RCNN. So these are regions of interest. You have one input vector for each region of interest. Or it could be raw pixels and the vision transformer, maybe giving you 144 patch embeddings. We have these features, and they are combined with a position embedding and sometimes also a modality marker to say whether it's visual input or linguistic input. So this is one side of the data. And then on the other side, we'll have our language data, which is typically going to be things like sentences that have been tokenized using the tokenizer of the backbone language model. In this case, in this paper Lexmert, it would be something like BERT tokenizer. So we'd split this, and then we can also mask some of the data. And then the vision and language BERT model jointly processes the visual data and the linguistic data. Exactly how this works depends on how the model is defined. And there are three really common building blocks for creating these vision and language transformer models. There's the so-called single stream approach, where the transformer blocks have self-attention operations that operate jointly over a concatenation of the linguistic inputs and the visual inputs directly. So it's doing full self-attention all of the time, trying to fuse these representations. There's also this approach of having a dual stream model, and there are two variants. There's the intramodal dual stream, where within each modality, the self-attention operation will only work over other inputs in that modality. So you can see here on the left, the language inputs, the W inputs here are only self-attending amongst themselves, and the visual inputs amongst themselves. And there's also this idea of having a dual stream intermodal processing, where you'll take, let's say the one on the left-hand side, the linguistic stream of the model. We're taking queries from the linguistic stream, but we're taking keys and values from the visual stream. And so when we do dot product similarity, we're trying to determine what's the affinity between this word representation and the different visual embeddings we have in the model. And then we're going to drag features from the value representations and fuse them directly into our word representations. And we're simultaneously usually doing this in the other direction as well. We're fusing words into visual representations. So you can see this as the model trying to do some kind of rich binding of data at different layers within the model. And it's also maybe slightly more controlled binding than the single stream full cross attention that's happening at every layer in the model. And so in terms of how these have typically been built into architectures with these single stream approaches, just to be very clear, we have things like our stream of words, we have our CLS token and our separator, we have our language embedding layer, and then we'll have our image representations. They could come from faster RCNN regions or VIT embeddings. They'll go through this multimodal transformer in a single stream version where everything is kind of richly embedded all the way throughout. And then at the end, we get a sequence of output embeddings, which represent a CLS representation or the different word representations or the different image-based representations that are now supposed to be, or hopefully, richly contextualized. In the dual stream setup, we typically see models that, first of all, have these unimodal layers. They are initialized so that they process just the textual stream independently, and then just the visual stream independently. So for the textual stream, it might be something like the first K layers of a language transformer. So if it's BERT, it might be the first 6 layers of that. And then after that, you'll have a series of multimodal layers, which might also be initialized from BERT, but you're going to do cross intra and intermodal fusion amongst those layers. So you can see, and you'll probably have settings where the visual features are also processed by transformer layers, but they're randomly initialized. And then they do this kind of fusion across modalities and then fusion within modalities. And this gets stacked over and over within the model in the attempt to try to learn these richly contextualized representations. Now might be a good time, since we're going to dive into all of the different models that I want to cover. So I think we're also going to do some kind of group photograph at some point. Is there an announcement? And no, we can have questions after, it'll be fine. Unless there are burning questions. I think there's burning desire for coffee and cakes.
Okay, so just an announcement then. So coffee break this morning will be on the North Garden, not the same one where you have coffee break in the afternoon, the one on the other side. It's north. Okay, so it's exactly this one. Sorry about that. So it's the same garden where you had coffee break last afternoon. Okay, so and after that, there's the group photo.
Okay, guys, come on, come in, sit down. So please, we're going to continue now. Just a reminder, today in the labs, we have recovery labs. That means that we're going to work on the previous days, right? So if you're interested in repeating exercises, things you didn't complete, come to the labs and we can help you there, okay?
Hello, welcome back. So we had just finished discussing this high-level overview of the 2 main approaches to building vision and language models using transformers. I started by explaining there were these 2 main approaches, cross-encoding and dual encoding models. And that at a high level, a cross-encoding model is going to take features from each of the modalities and learn through the transformer architecture how to fuse across these different representations. We also discussed that there are these different building blocks that can be used, and the building blocks mainly represent whether the model processes all of the data simultaneously, that's a single stream model, and then the two different types of dual stream models. One of the first vision and language transformers was catchily named Vilbert, and this is a dual stream transformer that's initialized from BERT. And you can I have a pointer, allegedly. Yeah, okay, game changer. So here we have our text processing, and if you've used the transformers library, you already know that these are what your tokens are going to look like. And then we have our embedding layer and position embeddings, and then we have a transformer blocks. And these were initialized from the BERT model. And then there's our visual representations. These come from the faster RCNN object detector that I mentioned before the break. So here they're using between 10 to 36 regions of interest, and these are embedded. And then there is this kind of co-transformer layer, which is doing this fusion across modalities that I just described. And then it's doing only fusion within a modality. So it's kind of like, oh, image word features, tell me what you might know, and then I'll try and remember stuff by myself. That's my mental model. And at the end, we get a sequence of embeddings for each of the different modalities independently. This model was pre-trained on the conceptual captions dataset. According to the paper, I think they got all 3.3 million image examples. And it was pre-trained on 3 tasks. So there's a masked language modeling task, which you all know, where we have these masked tokens in the input, and we're trying to predict the probability distribution here. There's also a masked region classification task happening over the visual data. And then there is an image text matching task, which is happening down here, given the representations of the CLS. Well, this is the CLS for the vision part, and then we have another special token in here for the language part, even though at the end they're jointly processed. And we want to determine if this is an aligned or not aligned pair. And so how this works under the hood is that the masked language modeling is identical to BERT and friends, except now the expectation we're taking is over these sentence image pairs from our data sets. And when we're trying to model the distribution over the masked word, we also have this visual data that is hopefully going to provide a strong clue about the identity of that masked token. You can understand for some words it might not be too informative, like and, but maybe a word like bear or horse or running, this could be useful information to help improve the quality of that prediction. The masked region classification can be formulated in a few different ways. You can either do a mean squared error regression directly onto the feature vector that should have appeared in the input, or you can try to predict a probability distribution over the object classes that the faster RCNN model knows about. Both of these variations are tried and explored in many different types of vision and language models over time. Which one seems to work best? I have always been a bit confused about this, but generally speaking, I think people combine many variants of this together. For the image text matching objective, this is just like next sentence prediction from the BERT paper, where there's a 50% chance of randomly sampling a mismatched sentence when you're doing pre-training. And here we're just trying to correctly predict whether they are an aligned pair or an unaligned pair. And the 15% masking that happens, as is shown on this figure, is usually across the modalities. So we're not doing 15% in one and 15% in the other, but that can change as a variant in different types of modeling approaches. So then you might end up masking much more data than you'd expect. And having 10 to 36 regions of interest as our visual features and using something like conceptual captions means that the number of inputs you'll typically process here for pre-training is maybe between 50 and 60, which is quite reasonable and manageable. Whereas if you were to use one of these vision transformers with hundreds of patch embeddings, you can see that you would maybe encounter some computational difficulties. In 2020, this is going to be chronologically through years. It's a biased sample. There's probably about 8 million models on Hugging Face. I can't cover all of them. This is an example of a single stream model, which was also initialized from BERT, and it also used visual features extracted from faster RCNN. In this case, it was now trained on more data. So we have the conceptual captions data set. We also have visual genome, which I mentioned before the break. We have the COCO data set, not using the object masks that we saw with all the sheep, and also something called SBU captions, which is an older data set of data harvested from Flickr. And there are some architectural changes here, for example, how the image features are embedded. You can also see now that we're making very clear that there are location features that need to be processed. This is typically, well, it was typically tackled by taking the X and Y position of a bounding of a region of interest, and then its width and its height, saying this is a concatenated 4-dimensional, or if you include other information, 5-dimensional vector, and then embedding this into the sacred 768-dimensional space. So you can do an element-wise addition with the image embedding. And in this case, the model was trained with some similar objectives to the ones we just saw. So we have MLM, MRC, image text matching, and then now we also have this word region alignment objective. And the goal here is to estimate an alignment between the text image. Hello? Did I hear myself, or does somebody have a question? Okay, I'm not going crazy. So the aim here is to estimate this alignment between the text representations and the image representations as embedded in the model. And this is operationalized as an optimal transport problem, where you want to minimize the cost T of transporting the embeddings from their image regions to the word embeddings. And this can be seen as kind of a fine-grained image sentence matching problem, where you don't actually have direct supervision about how to do this. All you want to do is minimize this cost, and you're going to have this cosine distance between the possible pairs of embeddings. And this was shown to be a really useful objective for learning better alignments at a finer grained level, rather than just do this image and sentence pair match. We want to go much deeper than that now. In 2021, missing all the other papers in 2020, there was an approach called VILT, which was a single stream model that was initialized from BERT. You can see a common theme here. And in this case, the visual features were extracted from a vision transformer. And because we were all here before the break, we know that VIT-B32, we know what that means. We're all experts. We know what the patch sizes are going to be and how big that model is. And this was pre-trained on conceptual captions, visual genome, COCO, SBU captions. This has now come to be, I think, collectively known as the 4 million data set. You'll often see this if you read more up-to-date papers than 2021, where they train a model on 4 million examples. It's usually this set. Here we have masked language modeling, image text matching, and a word patch alignment, which is also something that they try to optimize using optimal transport. There are a few kind of interesting quirks about this. So it didn't work if they initialized it from the vision transformer. It wasn't enough to learn about language just from image captioning data, at least in this particular model. And they also found that some of the formulations of the pre-training tasks, like trying to predict the pixels in a masked image region, did not help performance whatsoever. They didn't have an objective directly focused on modeling that type of data. That was just a regression task, but they said that it caused the model to lose its performance. So as you can see, we're now kind of converging on a similar set of pre-training tasks and a similar set of data sets, but we're innovating somewhat in terms of how we represent data. In 2022, we saw a model called Flava. This is a dual stream model, which has many different layers and many different components. So it's got independent image and text encoders. So our image encoder here comes from B16. So we already know we're going to have many more input patches. And there are tasks that are specific to modeling the image data. And that's shown here with these vision task heads. And then over here, we have our text encoder. I don't entirely remember what it was initialized from. It's probably some variant of BERT. And we have NLP specific task heads that can be put on at the end, or we can have pre-training tasks which only deal with textual data. And then we have some multimodal layers here in the multimodal encoder, where we're doing this kind of pervasive cross-fusion through the modalities. And from there, we can also have multimodal pre-training objectives. And at the end, we can have task heads that are specific to where we need to process multimodal data like VQA, which we discussed earlier, or in this instance of the figure, the hateful memes data set. And so one of the other innovations here, well, one of the noteworthy points is that they pre-trained on a data set of 70 million examples, which they claim were publicly available. They called this PMD 70 million. And there are many different types of data sets included in this, including things like captioned images from Reddit, captioned images from Wikipedia, all these types of rather varied and diverse sources. In terms of some of the additional modeling perspectives that they brought here, they included this idea of doing masked image modeling. So I just said that in the Wilt paper, it wasn't a good idea for them to do the regression to the feature vector directly. And so what they do in Flava is immediately after the image encoder, they have a masked image modeling task where the tokens come from a discrete variational autoencoder called byte, which was pre-trained on a different task. So given an input image, for example, of a cute dog, we can tokenize each patch in the image into a particular visual token. I think that byte has a vocabulary size of maybe 8,000 discrete tokens. And so then you can try to optimize directly on predicting which visual token should be associated with a region, and that the discrete variational autoencoder is going to assign similar visual tokens to patches that look similar to each other. In addition to this, they also have a contrastive loss, which happens on the CLS embedding of each of the unimodal encoders, so down here. And then in addition to that, we'll also have things like an image text matching loss, which is going to happen on the output of the multimodal encoder. So it's a step forward in terms of how many different pre-training tasks are happening and the level of separated learning and multimodal learning that's actually happening throughout this model. And in the experiments, because they have this separate image encoder and the separate text encoder, they also show how well the model performs on vision-only tasks or NLP-only tasks. I believe that it doesn't perform quite as well as standard language models at the time, but you can learn something useful through backpropping from the multimodal encoder into the text-only encoder. And if we come all the way up to 2023, then one of the most recent papers that I think is worth noting is Instruct Blip. And so multimodal learning is now coming fully into this instruction tuning paradigm that has grown in a great deal of attention over the last year in text-only NLP. And so this is a model that is initialized from something called Blip2, and it uses a vision transformer base and a FLAN-T5 language model. And the way that the model works here is we have this input image, which is embedded through a frozen image encoder. And then they have a layer that they call a Q-former. And we have these learnable queries, which we're going to use to transform the image encoding into a set of output embeddings. And in the Q-former, we also have this instruction that we're going to embed directly there. So the model is not only learning about the instruction as an input to the language model as a prompt, it's also extracting visually grounded features with regards to that instruction. And this model was instruction tuned on 13 data sets, and it was evaluated on 13 other data sets, sometimes where the tasks were unseen or where the task type was seen, but the data set was not seen. They manually constructed 10 to 15 task templates, as you do when you do instruction tuning. And there have been a lot of other similar models to this that have appeared in a very short space of time. And so you can maybe see this as the kind of vision and language worlds really starting to collide now, where something from NLP, this idea of the instruction-based tuning, it came very quickly into multimodality. We didn't have this multi-year delay anymore. And this model is evaluated on some of the common tasks like visual question answering. You can also frame things like retrieval through this type of framework. They also try to answer things like high school questions, like mathematics questions that also have visual inputs as well. So I think that this is a real representation of where the field is going, one of the exciting directions which we could see things traveling in the coming years. So that concludes the cross-encoding models, but maybe before we briefly talk about the dual encoding models, are there any questions about cross-encoding approaches? Or is it all perfectly straightforward? Okay, seems like you already knew everything. So the dual encoding models have emerged as what is claimed to be a sample efficient alternative to cross encoding. In the dual encoding framework, we typically have a backbone where the language encoder and the vision encoder are separate and they do not interact with each other. The CLIP model is probably one of the most well-known instances of this, but going back to 2019 and even earlier, we've seen other versions of dual encoding models. For example, there's a paper from Connell 2019 where they tried to learn a dual encoding model over speech and visual data. So this idea, it's not necessarily invented in 2021. The most popular instance of this would be CLIP, which is a 12-layer transformer encoder. We typically would use either a VIT or a ResNet to represent the visual data. And the model is trained to maximize the similarity of the embeddings of paired examples. So going along this diagonal. And this is something that's done on a large collection of 400 million image text pairs. The description of how those image text pairs were collected is quite brief. I think that there are some attempts open source to reproduce that web image text data sets. And then things like Lion have taken this to a more extreme level with much more data. The types of things that people have used CLIP for so many different things. It's such a versatile way of modeling data. One thing that you may have seen is people using CLIP for image captioning, where you encode an image using the CLIP encoder, and then you have this idea of a mapping network. This mapping network probably seems quite familiar now because we just spoke about the learned queries from the Q-former. This is the same basic idea. This is going to be used as a set of prefix embeddings to a GPT-2 language model. And they're only going to train this mapping network here. The CLIP encoder won't be trained, and the GPT-2 language model won't be trained either. So this is a question of how far can you get by using these large-scale pre-trained models. And I know GPT-2 is not large-scale anymore, but it was. And you can also use things like CLIP for evaluation. In 2021, Hessel and colleagues showed that the way that people typically evaluated image captioning models was to take an image, look at some reference sentences, have your model produce a candidate, and then do something like blur or meteor between the candidate and the references. And what they showed is that you can actually do reference-free evaluation using something like CLIP, and that this correlates quite well with human judgments, which was quite a surprise to me at the time. But now that I've used CLIP a little bit more in some of our research, I can just see how much it's really learned from its pre-training, and that this is a reasonably useful direction to try and move your research. And so, to summarize this description of some of the main modeling decisions we've seen, the cross-encoding approaches, we've seen many advances in parts that contribute to the loss. So we have masked language modeling, or masked image modeling, or image text matching, or a kind of a global contrastive loss. We also have multimodal losses in there. And we've seen this shift from working with regions of interest vectors extracted from faster RCNN to vision transformers. This shouldn't be too surprising, since there's a kind of a chronological time in which vision transformers suddenly existed. In the dual encoding paradigm, we've seen excellent cross-domain transfer to a wide range of problems. And one thing that has been quite constant is that we get better performance from larger models trained with larger data sets. And so one of the questions I'd like to pose now is, can we offload some of the training budget for our vision and language problems by using retrieval augmentation? So maybe we don't need to learn everything in weights. Instead, we can learn how to retrieve the information just as we need it. And this is a piece of research from Rita, who is a student Toronto or Copenhagen. And so the standard approach to image captioning is already explained so far, but we'll take an image encoder like this, and we will put it through a model, which is a skinny pipeline, and generate a sentence. And what Rita believed was that we could improve image captioning if we would jointly encode images with sentences that might describe the image. This is a difficult problem to think about because we're not really supposed to have those sentences. We're trying to generate images, captions for images we've never seen before. And so we're going to lean on data stores that store vector representations of our textual and visual data. And from this, you hypothesize that we can generate better captions, or that we can generate captions while maybe not training as many parameters as other approaches. And so this is an instance of retrieval augmented modeling, which has been used in a wide range of settings in core natural language processing. This example here from 2021 was about improving text generation by conditioning a model on retrieved examples. And this is for question answering, where you maybe have a question like, where was Alan Turing born? And you have a data store where you have a collection of sentences or documents that are encoded as passage vectors. And from this data store, you retrieve a set of passages that look likely to be an answer to the question. And the way this would typically work is you'd measure something like the cosine similarity between the embedding of the question and the embedding of the passages in the data store. And these would be inputs to a generative language model, which would then hopefully produce better outputs than just trying to answer this question directly and assuming that your model is large enough to have stored this piece of information in its weights. And so Rita designed this model called an encoder with cross-modal representations through retrieval augmentation. And so it starts with a vision and language encoder, which is already a bit weird for image captioning, but this is how we're going to do it. So you'll have your input image, and you're also going to encode retrieved captions. And there can be 1 or 2 or 10, depending on how much GPU RAM you have available. And then you're going to learn the kind of rich cross-encoded representations to give you a set of output vectors. The retrieved caption is found in a data store, like I just said, where the data store contains captions, but we exclude any captions that actually do describe this image in terms of their gold standard alignment in our data set. And you can see from here, we're going to measure some distances, and we're going to pick the captions that have the lowest distances. And these will be the inputs. And then our autoregressive language model as a decoder, which also has the cross-attention layer, is going to attend over the richly contextualized retrieved captions with the images to produce, hopefully, better descriptions than just looking at the image itself. The joint encoder is based on, is that a question? Yes. The question was, how many examples do we need to provide to get a good caption out of it? Thank you. It's an important question. The answer is more than one. In maybe 5 or 6 slides, I'll show you the results of what happens when you retrieve more. So what we found is that sometimes only picking the first example is a bit greedy, and it might not be correct, but the other examples tend to be quite good. So where were we? Yes, so it's the Lexmark model, which we didn't discuss, but it was one of the images I showed you. So it's a vision and language encoder. We use 36 faster RCNN regions of interest as our visual inputs. And then for the language inputs, we have K retrieved sentences. And in total, there are M different subwords across these different sentences. And we use the BERT tokenizer because that's the backbone language model that we have. And this is the joint representation that's formed. The retrieval system is based on something called FICE, and the captions of the images are represented with clip embeddings. So this is how we're going to try to operationalize this distance approximation. And we're going to retrieve the K nearest neighbors from the data store, where the image embedding using clip is compared against those data store captions. We used FICE because it's quite fast for our needs, and you can also train things like compressed data stores so that if you have huge data sets, you can also do some work with it in that direction. And our decoder is a GPT-2 style language model where we added in additional cross-attention layers. So as you know, the GPT-2 language model doesn't have cross-attention, but it's a transformer block, and you can just do a little bit of surgery and add one in, randomly initialize it, and then you can train it for your task. And the decoder here is going to predict captions based on the previous tokens it predicted, and also these vision and language encoder embeddings that are produced from the retrieved caption and the input image. In terms of our experimental protocol, the model was trained on one GPU with 32 gigabytes of RAM, and we trained the encoder and a randomly initialized 4-layer decoder. The retrieval augmentation came directly from the data store. It never saw any gold standard data during training. It never told it which sentences should be correct from our annotations. And we evaluate using common metrics for text similarity. I will only focus on CIDR here, but the results are similar for the other metrics. And we also see similar improvements when we train with cross-entropy or when we do additional training with self-critical sequence learning using the CIDR metric as the objective. In terms of the results, there's quite a lot to unpack, so I'll try and step through it. So Extra, which is the model I've just been discussing, is here in orange. It uses faster RCNN features, a GPT-style language model, and the vision and language encoder for LexMERT. We can look at some other approaches. Here's ClipCap, which uses just this lightweight embedding layer that's learned, uses a GPT language model and a vision transformer. We can also see here, we have things like the bottom-up, top-down model, which is faster RCNN features with an LSTM. Or here we have faster RCNN features with self-attention and lots of other cool stuff happening. We can also see a model that uses faster RCNN features. So all of these features are kind of the same as what we're using, but with a dual decoder that decodes and then redecodes. And so Extra performs quite competitively compared to the rest of these models. And it does this through the retrieval augmentation process, which all happens automatically. It doesn't outperform what was the best task-specific model at the time. This used clip visual features, which turned out to be much better than faster RCNN features. And it also had this dual-stage decoder. We can also see that Extra performs competitively compared to the visual language pre-training model, but not compared to Vinval. These are both faster RCNN-based models from the time. If we compared it to other vision language pre-training models for captioning, their scores would now be something like 152. And I don't know how to contextualize that because that's so far beyond human level agreement that I can't really think about it. But overall, this showed the promise of the retrieval augmentation framework. And if we look at some qualitative examples, which Rita picked, we can see here this is an image where in the data store, the model does a good job of retrieving captions that could describe it. And we've highlighted here in green some of the phrases that are particularly useful or relevant. And the final sentence comes out as a parking meter covered in snow next to a car. I don't know, it's almost there. Maybe it's the other way around. And then in the other perspective, we have this image of a cat, I guess, in a fruit bowl. So a kitten is stuck in the white basin, a very cute cat sitting in a sink, drinking from a cup. So this is clearly incorrectly retrieved information. A cat sitting in a sink over a cup of something. A white cat is lying in a sink. So some of the information is correct and some of it is really not. It seems to understand some of the important concepts, but not really how they come together. The model generates a sentence, a cat sitting in a sink next to a bowl. It's almost there. It just doesn't understand the importance of prepositionals. And to bring some data to the question that I answered earlier, the retrieval quantity matters, probably as a fact that the retrieval quality matters. So we can see here that going from left to right, if we retrieve a random caption from the data set, then the performance is the worst. It doesn't seem to know really how to use this. It probably just ignores it. If we retrieve just one caption, the performance is actually worse than embedding an empty caption, which would just be CLS and then separator. If we retrieve 3 captions, performance improves, and then I think we encode 4 or 5 captions in the final model, and we get the performance here at 121. And you can see from this example here that if you only retrieved and used the first caption, a man crosses a street under an umbrella and carrying a little boy, this would be misleading to the decoder about how to describe this photograph. But by encoding more captions that are retrieved, we can see that there is some important and correct information there, talking about the fact that there's a kid in an umbrella, or that the kid is crossing the street. Sometimes they even get information like that it's a black and white photo instead of a color image. So I hope that this brings some more evidence to the question you asked. We can also ask ourselves, what's the ceiling here? How well could we do? And so we set up an experiment where we use either the retrieved captions or the reference sentences as the input to the vision and language encoder for evaluation. And so we can see here that you can get a nice improvement when you've just done standard training and then you use these reference sentences for evaluation, which suggests there is room for further improvement. But one thing it also suggests is this is the COCO dataset, and there are 5 sentences per image. Even when you give it the correct sentence in an input, the models still won't get maximum performance. There's still some kind of limitation in terms of what's possible in the language generation model. I believe there's another question.
Yeah, it's a really smaller question, because you mentioned algorithm. So what is the side of the reference that compare to each other?
I don't know off the top of my head, but I know where to find that information. So I will get back to you later. CIDR is kind of an unusual metric. It doesn't have a kind of scale that we would like it to have. If we think about bleu, then we know that if this was perfect, it would be 100. So it's 60 points away from being the perfect output, according to the bleu score. Okay. In terms of trying to understand how this model works, we can think about what's happening in the attention mechanism in the decoder. And so Rita did this really nice analysis where for each time step in the decoder, we try to look at whether, and each layer in the decoder, we look at whether the model is on average paying more attention to the visual output embeddings from the multimodal encoder or the textual output embeddings. So what you can see here is that the first layer of the transformer encoder, it's paying a lot more attention to the visual than at later parts. It always pays more attention to the textual data, but as we get deeper into the transformer model, and thus we're closer to where we need to actually predict a probability distribution over the next words in the sentence, the model leans much more heavily into what can be found by looking at the textual embeddings in the multimodal encoder. For me, I have a story that makes sense to me, which is that, first of all, the model needs to figure out in the decoder, what is this example about? And then it wants to know how it should realize this as a word that it can emit from the language model. I hear you saying, but this attention isn't an explanation and none of this works. So we also tried some other examples to see what would happen. So if we have an empty caption as the input, the behavior is completely different here. This is where we just have a CLS and a separator. So now the model leans really heavily into the visual output embeddings from the encoder, because there is no information for it to grab from CLS SEP. And we also see the same thing for when you embed random captions. The model leans really heavily into the visual features at every step, every layer in the transformer decoder. And this is happening across most of the examples and at all steps in the model. So it really seems like the model is doing what we expected it to do, which is to look at some of the visual data and look at some of the retrieved information as it's decoding. And so in this part of the lecture, I've explained how we can address image captioning as language generation that's conditioned on multimodal inputs instead of just visual inputs. And these multimodal inputs come from retrieved sentences. This approach outperforms similar models that only process the image independently. And some of the ablations and analyses hopefully reveal that when better performance is found, it seems to be for reasons that kind of make sense about how the model is processing the data that's available to it. And so let's go even further. Can we train using retrieval augmentation with fewer parameters? Here, we initialized a GPT-2 decoder, and we also fine-tuned a vision and language encoder. Let's see if we can go further. So Rita, once again, thought that there's this big trend now in vision and language of training big models on bigger data, and an alternative that's emerging is to use independent backbone models and just train small mapping layers. We already spoke about this when I highlighted the ClipCap model, and that's one instance of this where maybe we have a pre-trained image encoder, a pre-trained language model, and we just train this fire block in the middle. And the main motivation for this piece of work is, can we go even further when we have retrieval augmentation in the process? What can we do with this mapping layer? Can we shrink it down so that we can leverage what we get from our retrieval system? And so through this, we end up with an approach we call small cap. It has a lot of different components, and I'll try and walk through them. So the first thing we have here is our input image, which is encoded with a frozen clip vision encoder to give us a set of output vectors. From this input image, we look into a data store and we retrieve 4 captions that might describe this image. So that's the same approach as last time. And with these captions, we have a prompt template that we're going to form where we start with similar images show, and then we have this sequence of sentences. And then we have a prompt this image shows. So we have this idea of kind of interleave, like a prompt template with a task demonstration. And then we have a GPT-2 language model, which receives all of this as input. And then we train just a freshly initialized cross-attention layer in the GPT-2 model, when we're trying to predict these unseen tokens. So these are the tokens that actually describe this input image. So now I've gone from saying we have a language model we initialize at random and a multimodal encoder to saying we just have a pre-trained language model, a pre-trained vision model, and we're just going to train this cross-attention layer. So we've already come down a lot. And we're also kind of assuming here that the GPT-2 language model or any other similarly trained language model is good enough at producing sentences that with the trained cross-attention layer, we're just trying to shift the distributions in the feature space inside the model so that it will actually produce these captions that we want to see. This is something that to me is still a little bit opaque. I don't fully understand how it does this correctly. It's one of these basic questions I have. So if anybody knows the answer, come and tell me later. That would be great. In terms of our experimental setup, we use pre-trained models from CLIP. We either use a GPT or an OPT backbone for the language model. We randomly initialize the cross-attention layer. We train the model only on the MS COCO dataset. And we do this in 8 hours using one A100 GPU. So it's less training time than the previous model. And we also have this really nice low rank cross-attention implementation where, so the full rank version would be where the dimensionality of our weight matrices would go into 64 dimensions for, I think, a GPT-2 base model. And this would give us 22 million trainable parameters. But we also experiment with having lower rank projections where we introduce a bottleneck down to maybe 16 dimension or 8 or even 4. And we can get down to as few as 1.8 million trainable parameters here in the model. In terms of the results, I'll try and build this into context. So these models here are the previous lightweight training approaches like clip-clap or eye tuning. Here we can also see this is GPT-2 base with a 16-dimension lower rank approximation. So this gets a performance of about 120 points. If we squeeze this down to 8 or 4, then we'll get down to maybe about 117 CIDR points while having only 1.8 million trainable parameters in the model. If we were to stick with D equals 16, so a lower rank approximation, but increase the language model size up to GPT-2 medium or GPT-2 large, we continue to get improvements in performance. And this is completely different from a model which uses a similar setup. So I think that this shows the overall effectiveness of this retrieval augmentation paradigm. And now we're not having a joint encoding in the encoder. Instead, we're putting the captions that are retrieved into the decoder in a task demonstration. And it does outperform other lightweight approaches, but you can see some of the huge models over here in the distance, and we'll just ignore them. We'll put them there and then just move on. And one of the really exciting things about some of the ablation analyses here was about the importance of retrieval augmentation. And so what we find, so the green line is red line is where we don't. So you can see that as you move towards these lower rank projections, the model without retrieval augmentation suffers drastically in terms of its performance, going from 112 down to 107 CIDR points. Whereas the model with retrieval augmentation, it kind of barely notices that you've really squeezed this projection layer between the pre-trained language model and the pre-trained vision model. And so I think this gives a really promising future on how we might be able to use these models with retrieval augmented learning. There was a question.
If I might.
Yeah.
I mean, I'm missing a bit of scale here. So you say you stated up the parameters and then get a better CIDR score, which makes sense, I guess, and sounds good. But it's like the increase in parameters actually worth the increase in CIDR, or it's like an increase of 107 to 111 actually. It's not not that like big of a deal in terms of cider, because I mean the scale is also from 100 to, I don't know, you said it's open, right?
It's not fully open. So going from something like 107 to 111 would be a meaningful drop in performance or a meaningful increase. That's something that you would probably think, oh, cool, I have a great new result. My new visual encoder did something, or my new training objective did something, and now I'm excited. Going from something like 116 to 117, it's not a meaningful increase. I think in the paper, we also have the bleu scores, which is a bit more meaningful. If you're familiar with bleu, I think that maybe you go from something like a bleu of maybe, I think it's maybe something like 34 to 35 and a half. And here we're at like 37.5 to 38. So you don't lose anything. You would just think, it's a random initialization. I'll do this again and see how the variance works out. No problem. Another thing that we can do is training free domain transfer, which I think it's a super nice idea. Our data store is just an object that exists on a hard disk. So we trained this model with Coco as the data store, but we could easily swap this for a different data store. And if you know something about the domain of images that you wanted to work with, you might say, okay, I'm going to swap to maybe VisWiz, which is a data set of images for visually impaired people who want to ask questions about images. Here, if your images if the sentences in the data store are of that domain, we can see that the performance for small cap is substantially improved compared to other lightweight approaches. And it also works for video data, like the MSR VTT data set. So we break the image down to a sequence and process it like that, and it still works by having this data store of information available. As a qualitative example, we can see here, this is an image from VisWiz. So from the MS Coco dataset, it retrieves captions like some carrots, potatoes, garlic, an onion, and some chicken broth. And I guess, yeah, it's a can of chicken broth, and it can probably see those vegetables in the image inside the image. The meal has chicken, bread, and coleslaw. This is the makings of a meal with chicken and vegetables. And so the end caption is a close-up of a plate of food on a table, which is a really bad description of this image. And if you were trying to use this as a visually impaired person, it would be very unhelpful knowing that you were holding a can in your hand. If we swap the data store to VisWiz, so this is the training data from VisWiz, not the evaluation data. It turns out there are lots of cans of Swanson brand chicken broths in that data store of captions. And now the model is able to generate a caption that more accurately describes what's in the image. And I know from looking through the Coco data set, Swanson is not a word that ever appears. The model has never seen what it means to be Swanson brand chicken broth. It's not been trained to do that. So maybe this is showing what the retrieval augmentation is actually doing. Maybe we're also leaning really heavily on the pre-trained language model, which sees loads of articles about Swanson brand chicken broth. I don't know. I haven't looked at that aspect of GPT. In an effort to make a huge mistake, why don't you, if you have a phone, open up your camera app and try this yourself. So this is a demo that Rita put online. You can scan the QR code. It's running and hugging face spaces. I think the model takes something like 7 or 8 seconds to produce a caption. So when a few of you have taken an image, I will also do it myself here. So this is what you should hopefully see. It might look a bit different on your phone. So I can pick an image. So this is from last night. It's definitely not seen this image because I only took this photo yesterday at about 10 p.m. This is, well, it's a beef sandwich that came at the end of a fish meal. Oh, so everyone's in the queue and it's going to take 409 seconds. You know what? We'll come back to this. I didn't quite realize the scale at which this would happen. So maybe somebody has actually got a caption out from the queue. Did anybody, who was the first person? You were the first person. Is that even remotely true? Okay, so the example seems to be a photograph of some ice cream with a strawberry sorbet, and it seems to have accurately described it, but it's never seen your photo. I assume it's your own photo. Yeah. In 385 seconds, we'll also see other retrieved captions. It seems to keep going up. Stop adding things into the queue. This was a major mistake. I'm going to get an email. Rita will get an email from Hugging Face and they'll ask her, what are you doing? So I tried this image this morning and it worked. So I was kind of like, yeah, okay, let's try it. It mentioned that there are some meat sandwiches on a table with a wine glass in the background. And I thought, that was pretty good. All sandwiches are meat in cocoa? I don't know. It's a good question. Maybe because it can see these brown parts and it associates that with being meat instead of aubergine. I'll come back to this in 380 seconds and we'll see what it says. Did anybody get a really bad caption for those of you who got one? No? You got an error message? That's a pretty bad caption. Did anybody else get a caption that they thought was somewhat relevant? Yes? The graffiti is on the tram in your photo. Okay, so it had some kind of localization problem in the image. Okay. Would anybody else like to share an example that they got, hilarious or not? Over here?
Her hand is not visible.
A woman with a stick in her hand, but her hand is not visible. So it's just a stick.
No stick, it's just her face and hair.
Her face and hair and a stick.
No stick.
No stick.
Yeah.
So hold on. What does your image look like?
A woman with a fish in her hand and the sun in the back.
Okay. So it's like did the woman catch the fish or?
The fish has got stuck in her hand. In her, sorry, in her hair.
I don't fully understand what that means. The fish got stuck. Okay. Let's just go with it.
It means that the fish is swimming in her hair.
Okay. Okay. And did the model do a good job with this?
At least it's right about the lady, and it has also in the retrieve captions there is fish in another sentence.
Okay.
But the main output is a woman with a stick in her hand, a lady that is on top of a snowy hill, and since the sun is visible behind her, maybe it's right. She's standing on a hill when
There's nothing else behind her but the sun.
Yeah, so I think you have already found the limitations of a fixed size data store.
Oh yeah, sure.
Yeah, so apparently there's a Slack channel and you can share these. I guess it will be funny. Okay, cool. I am position 10 in the queue. Maybe by the end of today, we'll get there. Okay, let's go back to full screen. Okay. So the demo is always online, but how fast it is depends on whether 65 people try to use it at the same time. So SmallCap was a much lighter weight model and it easily transfers across domains. Maybe if we had more images of people with fish, we would have been able to deal with that one. And we use a prompt-based conditioning method where the retrieve captions are used in this kind of task demonstration, and we just train the cross-attention layer. So we find we get nice performance in out-of-domain settings. And it's really quite a promising approach. Now we have as few as 1.8 million trainable parameters. But let's go even further. I'm not finished yet. Do you even have to train a model? Let's just go all in. Rita just keeps going. I was quite skeptical about retrieval augmentation when we started, but I'm completely convinced now, and I hope you are. So in 2023, there was this really interesting paper at iClear on Socratic models, where models communicate with each other through output labels. So let's take an image like this one here, and we're going to chain together different vision and language models. So the first one might be used to detect things in our image. And then the second one is going to be used to generate captions by filling in a template. So this is the template from the Socratic Models paper. I am an intelligent captioning bot. The image is a image type. There are a number of people. I think this photo was taken at XYZ. I think there may be A, B, C objects. And then a creative short caption I can generate is, and then the language model at the end generates these captions. And then you use a vision and language model to re-rank the generated sentences. So there's no training in the Socratic models approach. You're just using existing models off the shelf. And then you end up generating captions like this. So now we're kind of going all in on this Chinese room argument kind of idea. We have a model that looks at an image and produces a set of labels, and then it feeds these labels into the Chinese room, where instead of having this dictionary of English to Chinese symbols, we have this template, and then we're going to spit the caption out in the other side. And we're going to push this to its extreme, and we're going to try to do multilingual captioning with retrieval augmentation. So here we have on the right-hand side how the model works. So we have a prompt template, and within this prompt template, there are example demonstrations. So this will look like this. So similar images are described as, and then we have a list of sentences. A caption for this image in Portuguese is, and then we have a sentence that could describe this image in Portuguese. So we form a set of examples for the language that we're targeting, and then we have this input example where for the input image, we look in this data store of captions, which in this case is Coco. We use a multilingual clip model as the embedding space. From the retrieved captions, we now fill in this template, and then we have the model produce a caption for the image in Portuguese. So detecting things is going to happen in the data store of captions. Now we're not detecting things like objects and places and the number of people. We're just retrieving full sentences in English. We're going to generate captions using a pre-trained multilingual language model. And then you re-rank at the end using a multilingual clip model again. So we're just going to keep reusing this. And nothing is going to be trained by us. just using it. So in terms of our experimental setup, we use the XGLM language model in sizes ranging from 564 million to 7.6 billion parameters. The multilingual clip model from Lion. We do experiments on XM3600. This is a data set where we have 100 images in 36 different languages, where the images and the sentences are culturally relevant. They're not just people describing images that have nothing to do with their lived experiences. And so no training or fine tuning of any kind on any image captioning data. And the model gives really competitive performance compared to fully supervised methods. So these models here in blue, you can see for English that the best model here, which is trained on a lot more data. This is the conceptual captions data set translated into 36 different languages and used for pre-training. There's a boost in performance when you do this. But as you move down into other languages, we can see that the LMCAP approach, which just uses these task demonstrations, it performs quite competitively against these other approaches, even though it doesn't see the image and it just sees the language describing what that image should look like. Another interesting thing that came out of the analysis was that we needed at least a 3 billion parameter multilingual model for this to work outside of English. So when we have the smaller models, the performance in English continues to improve, but the performance in other languages like Spanish, Hindi, and Chinese, it only really starts to pick up when we have larger models. And this might be that in order to do this kind of prompt-based recontextualization into a new language, you need enough parameters. We don't have a full explanation of why it only works for larger models. So I guess I could just say it's a big model. And as a qualitative example, here are some retrieved examples of these people. So it gets it mostly right, the number of people who are in the image and what they seem to be doing. For the generated captions, the English caption is pretty good. I am told that the Spanish caption is acceptable. Does anyone speak Spanish? Is it acceptable? You look skeptical. Okay. And I've been told that the Chinese caption is fine. I spoke to one of our students and she said, this is totally fine. So yeah, we can leverage these pre-trained multilingual models and just prompt them directly without any need for training along the way. So what I want to conclude from this part of the lecture is that retrieval augmentation, it's a really powerful paradigm in vision and language learning. I think this is something that we can see coming in the next few years as a way for us to do research in university environments without needing massive models pre-trained on massive amounts of data. I've tried to show how we can train fewer and fewer parameters down to actually not training any parameters at all. And we can also take advantage directly of in-domain resources and larger pre-trained models as we go along the way when larger GPUs become available to us in most of our common settings. Okay, I guess we could take some questions. Are there any questions about this block of... Yes, we have a question.
What is the re-ranking part when it's, so it goes like vision language model, and then it goes language model to generate the caption. So I'm guessing that it takes the, it creates the detecting things, checks the data store, and then gets a set of things that it needs to talk about. And then the language model makes that template thing. Is that correct? And then there's a re-ranking after that?
So the language model takes the prompt as an input and we sample a collection of different captions from it. And then we use the multilingual clip model to re-rank them. So we take the input
Right.
image back in and the collection of generated captions, and we use this to measure which is the best caption generated according to mclip.
Right. So the mclip is just the re-ranking of it. Right. Right.
Yes.
Thank you.
No problem. We have a question here.
That you made sure that you didn't have the preference in those retrieved captions. Is that doing exact match, or how are you making sure that that doesn't happen?
When we retrieve captions from FAISS, we can link them directly to which image they come from. And so it's just a case of knowing this was image 14,260. That's not valid.
When you show the result for extra and which part is more important in each layer, like we saw that for vision it was always under, and for language it was always over vision.
Yes.
But then when you showed the results, the bad examples, it was like the propositional part, like where is this part? And also in one of the examples, the graffiti was on the train and not on, like, do you think that we can improve that, kind of maybe tuning that part of, maybe we should focus a little bit more, or make something that makes, or a hyperparameter that focus more on vision for a little bit and then go to language? Or
yeah, so I think we could. It's a good point. Maybe we could design some kind of additional regularizer that would perhaps push the model towards attending to different parts at different layers in the model. Maybe we could enforce the vision first. Say, until you're right at the end, you should be focusing more in this direction. It's definitely possible, and it's a good idea, but it's not something we've tried yet. Okay. We have a question up here.
Hello, thank you for the talk. On the first work that you showed today, well, not today, but in this blog, I'm just curious to know if you test the performance of using only the retrieved captions without the image.
Yes, we did. And it's not as good as having the multimodal encoder.
Okay.
Yeah, we had this question when we were working on the project. We did this experiment. It's somewhere in the paper.
Okay.
I'm positive of this.
Okay, thank you.
Thanks. Okay. We have 13 minutes to cover 50 slides. I can't see what could possibly go wrong. So there's going to be a part of the talk that we'll completely skip, but I'll continue on. So in terms of understanding multimodal models, I think there's a real interest in the community of going beyond benchmarking. So benchmarking is great because you can optimize one number and then write a paper and move on. But deeper understanding is something that it really drives my research interests. So we can ask questions like, are bigger models better because they have better contextualization of the multimodal inputs? Is that what they actually do, or is it something else? Or are these models acquiring certain skills? For example, they can do better counting, or they can do better localization. Are they better because they better understand linguistic structures, like these prepositional mistakes that we saw? Would this not happen? Is it something else entirely that we didn't expect? And the research here has been mostly focused on either model internal behavior, like attention mechanism patterns, or probing with tasks related to different skills. One of the first efforts in this direction was called foil captions, where people created data sets where they would have images paired with sentences, and there was something in the sentence that was wrong, but it was like plausible. So in this case, the foil is that people riding bicycles down the road approaching a dog. and it's clearly not a dog. And if your model understands this, that this is a bird, then you should be able to get some kind of understanding of, oh yeah, it knows that this is a different type of object. And so back in 2017, Shekhar and colleagues crowdsourced these types of data sets. And you could use this for different tasks, just like classification or FOIL word detection, or how you might correct this to be the expected output. It turns out that foiling has been one of the core mechanisms driving some of the understanding work. Most of the things I'm going to discuss now use foils as an example. So in 2020, there was this thing called the Vision and Language Understanding Evaluation, which is a suite of 5 tasks for probing models. There are things based on probing visual relations or visual co-reference, the multimodal fusion degree, the importance of different modalities, or the importance of linguistic knowledge. And there are many different types of things you can evaluate here. One of the things they found from this analysis was that the Unitar model, when it's doing cross attention, it relies more on textual features when it's fusing modalities than visual features as a basis on where the attention is being distributed in this single stream model. More recently, the VALS benchmark is designed to test specific visual linguistic capabilities with image sentence foil pairs. So you'll have things like this image and the correct sentence or the non-foiled sentence is a small copper vase with some flowers in it, and the foil would be just exactly one flower. And this might test things like numerical reasoning or quantifier-based knowledge. And so you can test your model in this benchmark, which has thousands of different examples. And what you can find here is when you do this kind of ranking-based evaluation where the model gets it correct if it makes the probability of the caption image pair higher than the caption foil pair, that text-only models like GPT-1 and GPT-2 are clearly not as good as some of the multimodal models. And one of the things we see here is with the 12-in-1, this is a variation of Vilbert, where it was multitask pre-trained instead of just pre-trained on 3 pre-training tasks. So we can already see that it was important from a kind of visual linguistic skill perspective to have seen many more tasks, not just about having seen more data. There's also from 2022 this idea of a vision and language checklist based on objects, attributes, and relations, where the goal was to evaluate vision and language models where we have these automatic manipulations to the data, where you might augment the sentence data or maybe the image data as shown on the right-hand side, and you can produce radar charts so you can see where are the strengths and the weaknesses of my different modeling approaches. You can also ask yourself, ask models things like how well do they understand the relationships between subjects, verbs, and objects. This piece of work from DeepMind created a data set where SVO triples were mined from conceptual captions, and then they crowdsourced images and captions that would fall into these types of templates. So you can do this with foil-based detection formulations to see what types of strengths or weaknesses your model might have. And none of these things have to do with it gets higher VQA score. This is a much more kind of lower level understanding. More recently, we've seen also the Winnow-Ground benchmark, where we have these image text pairs that evaluate compositional understanding. Like, is this an image of some plants surrounding a light bulb or a light bulb surrounding some plants? The images here were sourced with permission from Getty, and there are many different types of permutations in the compositional understanding required. I think the conclusion in 2022 was that vision and language models were not great at this yet. And this is something that, as a human, once you understand the sentence, you understand which image it should be paired with. So it should be a task that vision and language models would succeed at if they had the correct level of fusion within them. We can also look at whether models are doing vision for language processing or language for vision processing. by masking out different parts of the inputs in different modalities when we have aligned data. And we can see that when we ablate or remove parts of the input, that different models behave really drastically differently based on what they observe in terms of reconstructing the missing words in an input or predicting the distribution over the objects within those masked regions. And so we can see that while there's been a huge focus on task-based performance, there's actually a vibrant area of research coming out now on understanding how these models work beyond scores. And foil detection keeps coming up in this area. It's such a simple framework to collect this data. And we could also do this based on linguistic understandings and analyses of what we want to probe for. And I think you were also witnessing a kind of methodological shift going from attention-based analyses to more linguistically formed or skill-based analyses. In other words, things we'd like to see in our vision and language models. There are many different future directions here. We won't have time to cover all of them. The obvious candidate here is going to be text-to-image generation. This has exploded in its popularity, not only as a research area, but as a way of spending downtime and having fun. It seems like it's genuinely fun to generate images. There are two main approaches that have been pursued, either based on VQ-VAEs or conditional diffusion models. I think some of the big questions that we'll answer over the next few years are, do these models produce verifiably correct outputs, or do they just look plausible? Like, is it okay to have 17 fingers? Maybe. And how well can they deal with doing cross-cultural generation? Are they really focused on English-centric or North American and EU data? What happens when you try to generate data from different parts of the world? Also, this idea of maybe trying to go towards computational humor. One of the best paper awards from ACL last week was about trying to understand and explain jokes in something called the New York Times Caption Contest. This is a really interesting direction for work. It kind of goes well beyond literal meaning. This is a kind of a weak binding where you need a lot of context to understand this. And the fact that explanation should be generated, I think this will be a really interesting challenge. We might end up ruining our collective sense of humor forever if we actually succeed, since you'll be able to understand any joke at a minute's instance. There's also this idea, I think, of physical understanding. So like predicting and explaining physical actions will become important as we get towards creating more embodied agents. So like, given this video here, a question you might ask is, how many objects are prevented by the tiny green triangle from falling into the basket? This is actually really hard if you just look at this image as a starting point. But if you understand the question, you're probably already trying to imagine where these different things go and how that works. There was a data set in this direction at ACL 2022. For those of you who want to know the answer, there we go. So this is what happens as we move. I also think that there'll be some really interesting research in terms of multimodality and interaction. In other words, like learning to act in procedurally generated environments. There's this thing called the NetHack learning environment, where we can have kind of our visual representation in terms of this beautiful ASCII rendering, where you have things like, this is you as the agent, and there's a closed door, and there are tools along the way, and this is your status information. And so in this space, you could imagine all kinds of ways where we could perhaps use external knowledge to improve the performance of models, or maybe you can transfer this from one video game environment to another. But now we're going well beyond just working with photographs. I also think that multilinguality will continue to be an important future issue, since the majority of the work I've presented today is in English. So we need things like resources and models and evaluations to create useful multilingual and multimodal models. It's not good enough that we're relying on English data all the time. And so creating this high quality data will probably require time and money and community engagement. And these are all things that are in short supply in all of our lives. We do not have time to answer this question. It's just not possible. So I'm just going to skip through this. The main thing you need to know is that language and vision is the same thing. You didn't know it, but now you do. The results are really good. I'm sorry, I ran out of time on that. So to wrap up in the 3 minutes that we have left, I've covered what I think are 5 major areas of vision and language research. I started by assuming that you weren't experts in the topic, and I hope that you've been able to learn something across these different areas, data sets, representation and modeling, understanding, and new ideas in future directions. Where can you find research in this area? Unfortunately, everywhere. This will be you if you keep trying to find it. It's published in almost every major machine learning venue because you're working at the intersection of different topics. That means it's not enough just to look at things like ACL, NACL, and EMNLP. You have to be looking at CVPR and NeurIPS and ICML and ICCV and iClear and everything all the time. I don't succeed in doing this. And so that's why I have presented a biased view of vision and language learning today. I haven't presented every paper because there's a limited amount of time, and I already ran out of time as it is. There are surveys you can read if you'd like a different perspective on some of the core issues in this area. And I'll finish with some predictions and speculations. I think that we'll see an increasing societal impact of vision and language models, both for entertainment and misinformation. I think that we'll see a shift in focus from fine-tuning to zero-shot instruction-based models. Models like InstructBlip or Viper are in this direction, and I think we'll only see more of this happening. I think we'll see a more concentrated focus on understanding how these models work. We'll see bigger and better data sets that will continue to be major contributions in the area. And I think it will be a big challenge to evaluate bidirectional generative models when they arrive. And so my final reflection is that I think multimodality in vision and language is an exciting area of research. If you hadn't thought about it before today, I hope you will think about it in the future. We've seen big leaps in recent years powered by pre-training and bigger data. The areas itself, it's still in its infancy. I think there are huge opportunities for your ideas to make an impact in modeling and task creating, in understanding and in evaluation. And I hope that you'll think about that as you continue through your research career. Thanks. We have -2 minutes for questions. But I'm also here during lunch and stuff, so you can catch up with me then. Are there any questions?
I'll be really quick. You know how all of the retrieval models used CLIP as the vector kind of matching for the querying the relevance? Was there any attempt at using anything different or to train your own one, or would there be no point?
You're asking me to remember conversations that happened a while ago. I don't remember trying other embedding spaces. I think maybe we tried to use the embedding space of the encoder directly, because we already had a vision and language model, which has a joint embedding space. But the CLIP model, I think, was probably better than that. Did we think about training our own one directly? No, we just don't have the compute to do that.
Right.
It'd probably be a good idea, but we didn't have enough data or compute.
Yeah. Okay. Thank you.
Hi, so it's more of a general question than any concise one. So when you're working on vision and language, you have these very complex systems. You have pre-trained vision models, language models, you're retrieving your like a whole lot of stuff. So when something doesn't work or like the results are not what you expect, how do you go into debugging those results, or how you like fix the models or doing the next step? So like, how does that work?
Is it on there? I think there are many different things you can do here. One of the most important debugging steps is to figure out whether your model can process like really basic data. So there are synthetic data sets where they're not these kind of complex photographs. They're more like black and white images where you have different types of shapes and different sizes. And if your model doesn't work on these types of small data sets, if it's not able to correctly answer that there are 3 triangles in the image, then there's something fundamentally wrong with how you formulated your joint modeling problem. I think if you try to train a model on 15 or 20 million examples in pre-training and it takes 2 weeks and then it doesn't work, you haven't learned anything. But I also think that some of the understanding approaches I suggested, like these kind of visio-linguistic foils and probes, they can also be really useful to figure out, like, my model looks like it's working, but what's it failing at? So this, I don't have a straightforward answer. I can't say, oh yeah, just download this package from pip and it will solve all your problems. It's not that simple.
So if you're working with multilingual data sets, for the language parts, you can run some machine translation systems to do the translate testing. Are there any methods that you also translate an image to meet the culture that the language that you're trying to generate in?
What do you mean by translate an image?
I don't know. So if you do the translate tests for the language inputs, there's going to be a mismatch between the image and the language, because the image is from that culture.
Yes.
But I was wondering whether it is possible to transform or translate the image to meet the language that you translated to.
So I guess some of that data does exist in something like Marvel when a concept is shared across different languages in the data set. So like the basketball concept, we saw that that was present for all 5 languages. Would that be a form of translating the concept to a different language? By just having an image that represents that in a different language? Or do you mean something different?
I mean, for example, taxis in Europe, often they are yellow, but they are green in Japan. So if you see a car which is yellow in Japan, it's just a random car, not a taxi.
It's just a random car, because taxis in the UK are black.
Mm-hmm.
And they're a different shape. I guess that could be an interesting direction for working with something like text-to-image diffusion models. Can you edit exactly this part of the image and produce an object that's expected? And then does the model understand it better in that context? I think that could be a super cool direction.
Okay, thank you for your answer and the talk.
Thank you.
Hi, my question is, do you think, first of all, is there any work on more than 2 modalities? Like, I know that, for example, there's videos, and in the video, there's temporal information, there's audio. So what are the directions that you see in this?
Yeah, so there's like I said, this was a biased sample of the research available. There is work on working with video data, speech and text as well. You can find there's a nice piece of work from University of Washington called Merlot Reserve. It's a model trained on combinations of videos and speech and I think closed captions. And you can use this model in different kinds of settings based on the data you have available. I think they train it on YouTube data. And I think that, yeah, well, I've done some work on video processing like this in the past, and I think it's a really exciting direction. It also requires a lot more kind of data management and infrastructure to do this type of processing, because like you say, you have your video on disk, you have to process it. You're not going to process 60 frames per second. You have to do some subsampling. I think there are many different challenges there. What do I think we could get out of it? Better world models, like better models of what expected consequences might be to actions that are only described in text. I think that this would be quite reasonable, kind of like procedural knowledge. What could you do if you were faced with trying to prepare a meal, that type of thing? And there are data sets for trying to understand recipes, but these are only static images. I expect that if you learned from cooking YouTube videos, you would be able to do much better at processing that type of data. So I think that there are huge opportunities in that direction. And ultimately, if we're going to build embodied agents that walk around with us, then they'll need to do some kind of multi-stream processing like that, including also tactile inputs, which is something we haven't even covered here today. And that's because I don't think there are very many resources in that direction. Thank you. And then we need to see the sandwich. Okay.
Hi, thank you for the talk. So the idea of augmenting the image captioning with descriptions with the retrieval is very suggestive. I mean, especially when transferring to other, let's say, databases. And do you have a feeling, or did you do some experiments on how the size of the retrieval system, so the database, impacts the performance?
Yes, we did do experiments on this. If you combine different data sets together in your retrieval data store, you can get improvements, but it's not always the case. So it seems like there can be some kind of interference in the embedding space that's stored in the data store. And this is something that we're still trying to understand ourselves. But the answer is yes. Yes and no.
Thank you.
Thanks for the question.
Okay, so let's thank Desmond.
Not so good. I had another one.